Hello everyone, this is our fourth experiment in Design 2 Lab experiment. Today we are talking about HVAC control, heating, ventilation and air conditioning. If you remember last experiments, we did 3 experiments on a DC motor. So we did modeling, we did speed control, and we did also position control. So if you watch the videos, the last videos, you see the setup here is similar to the one we had last time. We have our system and then we have the controller, and we will send data between the hardware and software. So the only difference will be that is our device, instead of controlling the speed of a DC motor, now we are controlling the temperature of this room, this tube. We have a temperature sensor inside, and the actuator will be different also. In that system, the DC motor experiment, the actuator was the motor itself, and it will generate shaft speed of a specific RPM. In this case, our actuator will be this heater. This lamp will work as a heater, so in case we need more heat, the heater will be on. If we want to cool down, we have a fan on this side. We have a fan so that if we close the heater and with the help of the fan, the temperature will go down. So let's start our experiment. Basically, this is the same procedures we did last time. We go to our computer, local disk D, double click, and now we will go to HVAC trainer, HVAC, double click HVAC, and we see the software. We will start today with on-off control, and double click this. The live view software will open. Okay, this is our software. Same thing, we have an input, the voltage. The output is a temperature now, the time axis, and the values of temperature in Celsius, digital scopes, and signal generator to control the voltage, and some other parameters. So if you want to run this system, remember that we need to select our device. So this is device number 2, because this computer is attached to device number 2. If you sit in another computer, you'll find device 3, 4 or 5 or different device. So now the system is ready. If I run this system, I will find that I have in the output 2 temperatures. The blue one is set point. That means I want to control the room of that, the temperature of the room. I want to control it on the value of 23 Celsius. And at the same time, I have the measured value, the actual value by the sensor. It's fluctuating around, if I go down, if I zoom the y-axis to 12, for example, so it starts from 0 and then it goes up to the normal room temperature. So in this lab, the temperature is around 20, and that's why the sensor is reading the same temperature. But if I operate the heater now, if I allow the heater to be on, it's off right now. So if I click this, and you see that the heater will be on, the temperature will gradually increase in order to reach the set point or the desired value. And that process needs time. The only difference between the HVAC system and the DC motor system is that the DC motor, it has high response. So when you click anything, it immediately the change, you will see the change on the DC motor. But for HVAC systems, temperature systems, it has low response time, or it needs more time to respond. So you see that from 50 seconds up to 95 seconds, now we reach our value and the heater is off. Of course, you know that we can control our time axis, so let's start from 50, and you see that now in the beginning, the transient time, the temperature is rising, trying to catch the reference, and at some point we reach our reference point, which is 23 Celsius, and now the heater will be fluctuating sometimes on and off based on the need. So in this case, we are below the line. That means we need heat. That's why the heater is on. If we cross this point, if we intersect with this point, then the temperature will be off, the heater will be off. You will realize that. For example, let's just wait. Okay, now the heater is off because we exceeded that value, and because it was off, let's go back to 100. So you will see that the temperature is going up and down, up and down. Sometimes above the line, heater will be off. If we are below the line, heater will be on, as you see. So this explains the set point temperature and also the measured temperature. Of course, you know that we can change the amplitude. We can change the amplitude of our signal. So instead of having 5, we can say that, make it, so say +1. Sorry, this is not for voltage, this is for temperature. So we have amplitude, so now we, instead of 23, we have it 24. Instead of, now we will find it plus this, that means 30. So if I say 32, the limit, that means you will find our total temperature is high value compared to the 23, the first signal. So this amplitude is to control. Imagine that this is the remote control that you are handling in your hand, and you want to increase temperature. So that means this is 26 amplitude will give you some 29 Celsius. So let's go back to 0. Offset is the repetitions of the cycle. This is 0.08. If we make it bigger frequency, 0.08, you will find that the repetition will be changed. It has higher repetitions or faster repetitions, high frequency. Let's go back to 200. Now if you compare the cycles, it was 0.08 and now it's 0.05. You will find that the frequency, you see, it's changing very fast compared to that one. If we go back to 100, for example, and you see this cycle, this big cycle. So let me take it back to 0.008. Offset, it also controls the temperature. So if I say that offset again 0.75, you will find some step. You cannot see that because the zoom is not set correctly. So let me make this to 22 and this one to 24. Now you see that the offset is changed. This is offset. If I increase this, I will find another step. If I increase this again, I will find new step. So this is to control the set point, the blue signal set point. So let's stop now and go to our manual to see what's happening. Stop our experiment and go back to our manuals. It will be there in manuals and student manual for HVAC. Double click. So same as the DC motor, you will find that first page is to show the experiment in details, to explain the figures, explain the symbols, amplitude, frequency, offset, everything. And then we will have in-lab experiments. Section 1, on-off control. On-off control. So to start the experiment, we need to open the software, make sure we select the correct device as we did, and we run the system. Now the cooling fan is automatically, as you hear the sound, the fan is operating, is activated when the broadside power switch on the system is on. So the actual temperature TC in the scope, this is normal because when we run the system we have our set point and we have also our actual temperature. So we need to adjust the temperature scope because for the scales to see both reference and actual temperature, because maybe sometimes you will open the software and you find that this is starting maybe from 28 and then you say that and this is 32. Some people will say that we don't have any readings and we have some mistake. Actually the readings are below 28, only you need to check the scales on the scope. Good. So we need sometimes to calibrate the temperature. The sensor that we are using to measure the data, it's inside this room. So we just click calibrate in order to make sure that the readings are accurate, it should be in that side, the black, this one, the small black element. This is our temperature sensor. So anytime we run the system, we should calibrate the sensor just to make sure that the readings are okay. And now we activate the heater by clicking the off button so that the heater will be running, and now we will be ready to have our experiment. So we have some exercises. Before that, we need to make sure that our amplitude is 0, frequency 0.08 and offset is 0.5. So let's do that. 0, 0.08 and offset 0.5. We are ready now, so we can run our experiment. We have the scopes, we need to set them as you see. So let's go back to 18 for example, and leave this on 28 for example. So now our system is good, and we are reading, let's read only 100 seconds. Because the heater is on, we have temperature is increasing until we reach our set point. If we reach it, the heater will be off. Now it's on because we are below this value. Good. So exercise number 1, we need to examine the actual temperature and the reference temperature responses. So as you see, this is exactly what I explained. I have the set point is constant on 23, while the measure point increasing because we started, we are increasing temperature until we reach this reference point. If we have our red measured value above that, the heater will be off. If we are below it, the heater will be on. That's it. Exercise number 1, we want to vary the offset between 0.5 and 2 Celsius. How is the reference temperature T required is set? Attach a sample of temperature. So we can say that this is 0.5, and now I'm going to increase this to 1 for example, and let's just wait for 1 minute, 2 minutes to see the response after we change the set point, and we can go back to 200 starting from 0 because I want to see the full range. So now even if I increase the reference point, now the heater will be able to catch that value. Remember that it was on 23, now it's on 24. I change the offset 1. If I change the offset again to be, for example, and just wait, let's just wait for this to reach the reference signal. But the point is, even if we increase the offset to 2 for example, higher set point, higher reference point, you will find that the actual temperature is now increasing. It will increase until it reaches that value. But as we mentioned that temperature systems, they require more time to respond. It's not like the DC motor, you click and then you find the response. So now you see that the temperature exceeded the reference point and the heater was off, and again that we reduced because the heater was off, we have less temperature, and this is the process. So we can stop and take a screenshot of this graph to answer exercise number 1. So this will be our answer for exercise number 1. We studied the offset. The offset came from 0.5, 1 and 2 to have more different values. So if you want to go to exercise number 2, now we will study the effect of relay amplitude, the VH amp. So, and we should explain how the heater voltage affects the temperature variation. So this is the relay amplitude. Where is that software? Yes, it's here. So we want, now if we run our system, same thing, the same behavior, but let's go back. The offset, it was 0.5, the original offset, and we will study the effect of this relay amplitude. So I will divide the screen into 3 segments. So each 50 seconds I will put some value. So let's wait for the first 50 seconds, and they will have the VH and the relay amplitude will be 2.5, and then after a while I will change it to different voltage, maybe 3.5 for example, and then I will change that element to 5 to study the 3 elements. So now let's say that it is 3.5. We see that the voltage is increased right now, and the intensity of light, heat, is also increased because of that. And now you see that we reach the setter point faster compared to that small voltage. And now since we reach this, the heater was on, and then again we need more temperature, so the heater will be fluctuating between on and off, but it will take more time while it was on because we already have our temperature. If we increase this voltage into 5, for example, that means we have high volt, we have higher intensity, and now we will reach our value faster, and most of the time we are above this region, above the set point. And now you can see that this response, this region for the first value, this region for the second value, and this region for the third value. So let's go back. This will be the answer to exercise number 2. Now we want to explain the effect of changing the relay mean, the VHF. So let's go back to 2.5 and then start our system again. And also we can just calibrate to make sure that readings are perfect or accurate. So same thing. We are not going to wait for the full time, but in general the idea for temperature systems is that they need more time to reach the values. So we will wait 50 seconds for example, and then we change the VH off to 3.5 for example, different element, and we wait more 50 seconds or more than that, 100 seconds, and then again we change our VH off. If we say for example 5, so also same thing, you are changing, you are increasing the voltage, you are increasing the intensity of light, intensity of heat, and that's why you have more time, the temperature is above the set point. Stop. So exercise number 4, we want to examine the effect of changing the relay width delta TH between 0.01 and 1 Celsius. What is the meaning of this element, the relay width, which is delta TH? This element, if you see that we are, for example, let me control this up to 2.5 and starting from 22, 24, 21. So this is in the middle now. So what is the allowable increasing? What is the allowed overshoot? Can we reach 23 above 22.5? What is this limit? Delta TH controls the highest thing. So in the manual it says that compare 0.01 and 1. If we have it very small, which is 0.01, and let's go back to our readings. For example, or we can select any medium readings and we can start and calibrate. So because of this 0.01, very small value, the heater will be on and off, on and off, on and off, because we have the limit of 0.01 Celsius. This range is very small. But if I increase, so I will wait from 0 to 30 seconds, for example, and then I will change this to 1 as mentioned in the manual, and we will study the effect of this high value. So what is the difference? The difference is that you are safe because you are in the range of 1 Celsius. So if you go down 0.1, 0.2, 0.9 up to 1, it's okay. The heater will be off. The heater will be on. If you are going above that, you will go up until you reach this range of 1. So the fluctuation now will be different because here you have one small limit, and now you have the freedom to go +1, or it's kind of an error. This is plus or minus 0.01, here plus or minus 1, and this is the difference of that element. So if we stop and let's go back to exercise number 5. Now this is modeling, same as the DC model, DC motor model. So now the manual advised us to put these values: amplitude 0, frequency 0.08, and offset 1. 0, 0.08, and offset 1.5 as advised, 1.5. And then VHM 4, 4, and 0.5. So 4, 4, and 0.5. Good. Exercise number 5. So adjust temperature scope to see both reference and temperature. So 1, we cannot see. So let's go. I think this is good. 21 until 25. 25. Okay, we can see both of them. Good. So adjust the offset in the signal generator to obtain relatively symmetrical oscillations. So this is the oscillations. Let me just put it on 100. 100. 100, okay. I'm starting from 0. So this seems like symmetrical. So if this is 2, this is 2. That means this is a sine wave, approximately a sine wave. So we are in good shape now. Now exercise number 5, we want to observe the heater voltage and the chamber temperature as discussed in reference 2, which is the manual control guide, and we want to find the parameter kV, the model, the gain kV, that will describe the relation between the voltage input and the temperature output. So in order to find kV, you need to fill table number 4. In table number 4, we need to find something: delta T, the difference in temperature; delta V, difference in voltage; ramp time, the time needed to reach the peak, and we will find the ramp slope from this unit. So we will divide this value, this amount, divided by both voltage and seconds. So how we can do that? Simply, we go to our setup, and for example, I can stop this, or even before that, I can control the axis. We can stop. So now 0, I will take from 0 to 40, or 0 to 20, for example, 20. And I will control this to be 24, and this to be 23. So if you want to draw, let's take a slipping tool, and we take this. So if I want to draw, if I want to reach this peak, what is the temperature in here, and what is the time from starting until this peak? What is the time? So this will be our time, and this vertical distance will be our temperature. If I want to measure this, I need to go to the reference. Y-axis is 23.83, and this is 23.4. If I want to measure time, Tmax is something, 7 point something, and T0 is something. Of course, you can control the x-axis by changing this. So I will start from 6, for example, or even 5.5, and then stop at 9 to have a better range to study the readings. So if I'm able to calculate delta T and T small and voltage difference, it's 8 divided 8 minus 0, this is delta V. So simply I will go put this value in here and calculate the value of K, which will represent the model of the system. So this system has a gain K of a value something that we calculated, and this is our objective of this experiment. It is on off heating HVAC system, and the section we did in part A is an on off control with finding the model of the system. Okay, that's it, and thank you very much.